recording our show here for today. Next thing I'd like to say, of course, let's have our local weather forecast. Is it the fifth time, I think? The fifth time this year we've been under the chance of a weather event. We've been lucky as heck, and I feel sorry for our neighbors in the West that have not been so lucky as us, but we've been incredibly fortunate about where the weather has landed. Apparently, one more time, we might have weather on Wednesday. I don't pay that close of attention, but then I hear these things. I don't know if we'll be doing remote class or the on-campus thing will still be going on Wednesday. I don't know. It says tune into the Southeastern webpage and they'll let you know. So I don't know what's going to go on Wednesday. I have no life, so I'll probably be here whether it rains or not because I don't have a life. Okay, so then what we had been doing on Wednesday of last week was we began to look at the elements in combination. And again, first of all, there's like 115 or so building blocks of nature, which we call the chemical elements. And there are many applications of the elements as pure substances, many applications, but more often than not, we're all very aware that the elements love to combine with themselves. And we're not here to learn the motivation as to why, and believe me, it's well understood what motivates atom A of one element form to combine with atom B of a different element form. It has to do with the way electrons are distributed around their nuclei. Well, since I opened the can, let me at least just say the motivation and where it stems from. Let's, for the moment, just think of the electrons buzzing around the nucleus, kind of like when you put clothes in the washing machine. So when you put clothes in the washing machine, in particular, let's say you put a bunch of heavy, wet towels in the washing machine, and they all pile up on one side of the washer thingy, and it gets into the spin cycle, and the washing machine goes crazy. It's like wah, 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 dancing around on the floor and all that, because all the wet towel mass is piled up on one side of the washing machine. Now, what we call that as physicists, we call that angular momentum. And the angular momentum is out of balance inside the spin cycle of the wet towels of the washing machine. And it has this wobbly effect to the way the machine experiences the combination of forces acting on it. Now, if you stop the washing machine, open it back up, and spread the towels evenly in the machine, put the spin cycle back on, now it just hums real nice and smooth. That's because you have balanced the angular momentum, so you have mass on one side, mass on the other side. And now as it spins, it can spin these masses in a way so that the forces are all in balance. Okay, now why I'm giving you this analogy is to tell you why electrons like to combine, atoms like to combine with other atoms. And the point is that atoms with their electrons buzzing around their nuclei also possess this angular momentum. Most of the atoms in the table have wobbly spin cycles, meaning the electrons are distributed around their nuclei so that as they are in motion around the nuclei, it makes them wobbly. Now, as funny as that sounds, that's the simplest way to describe what goes on. So what atoms do is they either add more electrons in to balance their spin cycles, or they actually take electrons out to balance their spin cycles. So they lose the wobble. And this is a spontaneous process. When I talked about spontaneity, what I talked about this with you before in terms of other electrical processes of transfer of electrons. This is spontaneous as well, meaning these electrons these atoms are compelled to do this to make the angular momentum evenly distributed for the rotational motion of these charges around them. So, long story short, that's the motivation of almost every atom in the periodic table to gain or lose electrons. Now, having said that, there are a very small number of elements at the very edge of the table that have perfectly balanced spin cycles already. They have no desire to change their spin cycle. They love the way electrons are buzzing around them. As a result, they don't play these games. They never add or lose electrons. Now, having said that, humans have taken that as a challenge. And we have attempted to say, well, okay, I can make that thing take electrons, or I can pull electrons off that. So yes, of course, if we go to extreme means, we can force these elements that already have balanced spin cycles into losing or gaining. But under normal, everyday processes which occur on this planet, they never lose or gain. Now that only works for, again, about 8 elements, maybe 7 or 8 elements already come pre-balanced. The other 107 don't like the way the electrons are buzzing around them. Gives them a headache, gives them a wobbly nucleus. So the other 107 elements are always seeking spontaneously to balance the way charge is distributed around the nucleus so that they have none of this excess angular momentum, and they now spin smoothly, as if you like. Okay, so again, the elements that have the balance already are given a particular name by chemists. We call them either the inert gases, or we call them the noble gases. And these elements are all lined up at the very outer edge of the table, and they start in column 18 with helium at the top. And helium should be familiar to us because we like to use it in a variety of applications to make things more interesting on our planet. And they go down from helium to neon to argon to krypton to xenon to radon. These column 18 elements have no desire to lose or gain electrons. So they're, okay, and here's another very interesting point. It turns out that all of chemistry is what is the result of this attempt to lose or gain. So everybody else, the other 107 elements, are jealous of these 7 elements. And so the other 107 elements are constantly losing or gaining electrons in attempts to balance their washing machines and have electrons distributed around their nucleus, similar to how those particular 7 elements of the inert gases or noble gases are configured. Now, it turns out in the world of science that it is this property of loss and gain of electrons that defines chemistry. Chemistry occurs as atoms attempt to lose or gain electrons. In chemical reactions, this is pretty much what is going on. Electrons are being moved from place A to place B in attempts to balance these properties. So the spontaneity is the natural occurrence of these materials as they try to make magic numbers of electrons distribute around their nucleus. Okay, so that is the motivation for why there's loss and gain. And it is all of chemistry. The result of this action of loss and gain is energy loss and gain. It's property change. So after the elements undergo this swap of electrons between them, now they are at a higher energy or lower energy state. They might emit energy so that we can harvest. It might change the phase of the matter from liquid to solid, from solid to gas. It might change the properties of the metal or the material from something very stiff and rigid into something very pliable and workable, malleable, we call it, or ductile, so we can do things with the materials after these changes occur. It might change their aesthetics, like what color they are, how they appear to you. And so all these different results occur while the atoms involved are undergoing changes in electrons distributed around their nuclei. Really fascinating, at least to individuals such as I, who study these properties and try to make patterns out of these behaviors so we can understand, and we not only understand what's going on, but we can also make technological advances based on these kind of things that are occurring. All right, so what we also talked about on Wednesday of last week was the type of reactions that form, as we called them, ionic compounds. And as the name implies, these atoms have become ions when they lose or gain electrons. Now, the motivation, again, for the loss and gain is to balance the charge and motion around the nuclei. Some can do it by adding extra electrons in. Some can do it by removing excess electrons out. So when an atom, of course, adds extra electrons in, as we have talked about, it becomes an anion. It becomes negatively charged. Now, where does it get these electrons that it has added in? It does not pull them from under the rug of the universe. It doesn't get them from out of its pocket. When an atom becomes an anion, it has taken electrons from some other element. So simultaneous to forming an anion, something else has become a cation. So this thing that loses electrons, because of course, again, we don't fool around with the positive charges, we remove electrons to make a positively charged material. And that's where the electrons come from that other materials are gaining. But now after these two elements, we got two elements, we got element A and element B. Element B says, I want another electron. Element A says, well, I got an extra one and I want to get rid of. So A gives an electron to B, but now they can't run away from each other because now A is positively charged after losing an electron. B is negatively charged after gaining an electron, so they are stuck. And this sticking together of the two atoms forms an ionic bond. The opposite charge of the originally neutral elements now forces them to stick together, and they are now bonded together. And since this bond is a result of their opposite charge, chemists have called this bond an ionic bond. Now, as we also talked about, this doesn't happen in one unit of A and one unit of B. Simultaneously, it occurs in hundreds of trillions of atom A's with hundreds of trillions of atom B's. And then all the opposite charges just whoop, stick together in a big extended collection of plus minus, plus minus, plus minus, plus minus in 3 dimensions. And if enough of these plus minus, plus minus, plus minuses stick together, they become macroscopic, or they become visible to the naked eye. And that is what we call, ladies and gentlemen, a compound. A compound is when actually individually there wants to be an exchange of electrons between two single atoms, but ultimately it's an exchange of electrons between hundreds upon hundreds of trillions of them simultaneously, and they all stick together so that they make something big enough in connection that we can see with our naked eye. Now, again, I mentioned this last time, probably in order for you to be able to see it, you would have to have 10 to the 20 atoms giving an electron to 10 to the 20 atoms accepting an electron, and then they're all oppositely charged and all stick together. So that would be relative, basically the size before it's even the smallest perceptible grain of this compound. Okay, now since this occurs in salt, NaCl, and occurs in many other elements that are cousins of the sodium, that is the cation, and the chlorine, that is the anion in salt, we as chemists call anything that generally follows this pattern a chemical salt. So to a chemist, not only is NaCl a salt, but also KBr is a salt, also NaF is a salt, also MgO is a salt, and on it goes. Typically, as we talked about, you take an element from the left side of the table, which we classify as a metal, they become the cation, they combine with an element from the right side of the table, which we call a non-metal, they become the anion. Did I say that right? The metals are the cation, the non-metals are the anion, and they stick together and make the so-called ionic compound. Okay, after that lengthy 20-minute introduction to this concept, which again doesn't bother me. You got nothing better to do. I got nothing better to do. So I could ramble on about things we've already talked about in order to just reinforce some of these things we've already talked about. What I'm really doing is setting the stage, because not all combinations of atoms form ionic compounds. There are other mechanisms by which atoms combine. So I want to discuss with you today the competing mechanism by which atoms combine. And in this competing mechanism, we're going to give the resulting combination a different name. When the atoms combine in the method we talked about on Wednesday, we said they formed ionic compounds. Ionic because there's distinct charge giving and taking to make pluses and minuses. Compound because they stick together in incredibly huge numbers of units, concatenating onto one another. Now, today, we're going to look at this competing mechanism by which we can combine atoms. And I think to do that, what I want to do is go to my slides. So I'm going to hit the present thing, and I'm going to present my screen, I think, and I'm going to hit this thing, and I'm going to hit that thing, and then I'm going to hit this thing down here at the bottom. And oh no, I'm not going to hit that thing. I'm going to hit this thing down at the bottom, and I'm going to go to this thing that says, what's that? And I guess what we want to do then is dive in. Somebody help me. Did I do something wrong? We're still talking about charge and matter. I'm talking. We're now looking a little bit about how charge flows. How did I do that? That was weird. Boy, you know, it's weird for several reasons. It's weird hearing my voice, which I could never be a radio or television personality because my voice is ridiculous. Two, oh my God, am I old? God, I can't stand looking at myself. It's terrible. It's just terrible getting old. Wait till you guys get old. You'll hate it. That's a guarantee. Okay, anyways, I don't know what I was doing there. Somehow I hit record on something. I'm going to go back to my slides. Okay, I'm back on my slides. I think somehow I managed to hit myself playing my own video. That was really weird. All right, that's a first for me. I managed to do a lot of dumb things on this because of my lack of technology. But, okay, I hope now that we can see my slides on the screen, I hope. And again, the idea we're going for today is a different approach for atoms to combine. Now, which approach is more favorable? I can honestly tell you, it depends on what materials are trying to combine as to which approach they will take. Typically, when you're combining metals with nonmetals, you get the thing we talked about last week. You get the ionic compound. To get this new approach, it's typically nonmetals combining with themselves. And when we have nonmetals combining with themselves, we more typically form what I am going to call a molecule. Now, what is a molecule? As it says here, it is formed by elements that are combining, that instead of having very different desire to gain electrons, they have about the same desire. See, the key with the compound is one definitely says, I want to get rid of electrons. The key with the compound is one definitely says, I want to take electrons. So it's a clear-cut delineation of role in the game. You got a giver with a taker. The givers are the metals, the takers are the nonmetals. When you form molecules, you're typically putting together takers with takers. And so they're both wanting to take electrons, and they both kind of fight a tug of war for electrons, and it ends up that neither can win. So they say, I'm exhausted. Let's quit fighting over electrons. Let's just share them. So when you form molecules, rather than transferring an electron from A to B, A says here, I'll give you one, and B says, I'll give you one, and we'll put them in the middle, kind of between us. And then I'll share mine with you if you share yours with me. But we're going to share them in a kind of an agreement where you don't really own both of these. I don't really own both of them. They're kind of on the table between us. That's what we call a chemical bond. When you bond atom A to atom B, atom A lays an electron on the table, atom B lays an electron on the table, and they are common property to both atoms. When you have an ionic compound, atom A says, I don't want this, here, you take it. Atom B says, I want it, I'll take it. So then when at the result of that, you have a positive charge thing to a negative charge thing, and they have to stick together. So when you form molecules, technically you are truly bonding atom A to atom B by having them each share an electron between each other. Okay, so molecules are formed by elements combining with themselves or combining with elements that are nearby themselves in the table. Those are the elements that have the same desire or very similar desire to pull electrons to them. Okay, now molecules, it turns out, are different than compounds in another regard. Molecules exist as individual entities. They are not clustered together as the name compound implies. So let's think of some very simple examples of the differentiation between a compound or a molecule. When I shake salt out on my French fries, I am not shaking out individual NAs and CLs. I'm shaking out a bulk collection of a huge number of NaCls all stuck together. Now let's contrast that to a glass of water. Granted, there, just like in the chunk of salt, is gazillions upon gazillions of water units in the jar of water. But think about what you can do. I can put my finger down in there and I can move the water molecules. Well, I said the magic word. I can move the individual entities apart. If I try to stick my finger down in the salt, yes, I can put my finger between a pile of salt crystals, but if I want to put it into each individual salt crystal, I'm going to have to bust apart the crystal. I'm going to have to break the attractions between the NAs and CLs in each crystal to literally cleave each crystal. Now, again, I can easily part the water units in the glass of water because they are individual entities. Same thing is true in air. Air, of course, is a collection of units of atoms. The units of atoms in air are air molecules. Because, of course, I can easily part the air molecules from the attractions they exert upon one another and easily move through the air. So there's a hierarchy to intermolecular force of attraction when you go from one state of matter to another. It's pretty obvious that the cohesiveness of gases is very low. You can just essentially go through a collection of gas molecules as if you don't even know they're there. So that means that the cohesiveness they feel for one another is very low. So gas molecules have very little attraction to one another. They are individual entities. Now on the other extreme, let's go to solids. If I take this wall here in this blackboard and I push upon it, I have a hard time cleaving the interaction between the units that make up the solid wall. That's because there's so much force of attraction between the molecules that I have to exert ridiculous amounts of force to take them apart. Now I can do it, but I really have to put a lot of force in to cleave the attractions between the molecules. So as a matter of fact, one of the hallmarks of the hardness of a solid is how much force you have to apply to separate the attractions between the solid. Of course, we're all very aware there are certain solids that I can cleave much easier than others. So that says something about just how much intermolecular attraction those materials are exerting in their solid phase for each other. Okay, now think of the liquid state. That's intermediate to the gaseous state and the solid state. Unlike gas molecules, much like gas molecules, I can make my way through a liquid. I can slog my way through the liquid state. Now, of course, I think we're very aware that I have a little harder time slogging my way through the liquid state than I do through the gaseous state. I can just bop right through the gaseous state because the molecules have very low attraction for one another. The liquid, on the other hand, I kind of have to exert some force. Now, I can make my way through it, but I have to exert a lot more energy to disrupt the attractions that liquid molecules feel for one another. So, liquid molecules are individual entities. They do not form a solid which has so much connection to one another that I really have to work very hard to get them apart. However, of course, liquids are molecules, but they have much more attraction than, say, gas molecules. Gas molecules are nowhere near as dense, meaning they're spaced way further apart than our liquid molecules. And the origin of why liquid molecules are spaced so closely together is the fact that they have much more attraction between them. As a matter of fact, you might not be aware of this, but the spacing between molecules in the liquid phase is essentially the same spacing that the molecules have in the solid phase. The distance between individual entities in a liquid and the solid are about the same. Now, they do change a little bit when you change a liquid into a solid. And this might be surprising to you, but if you think a little bit about it in your freezer, you can understand this. If I put liquid water into my freezer, it solidifies, of course, as I lower its temperature. But the solid water takes up more space than the liquid water. Now, if you don't believe me, put a full bottle of water in the fridge, a full bottle of liquid water, and then after it freezes, I think you'll see that it's almost bursting. And sometimes they do burst. Sometimes you put a can of beer in the freezer to get it cold really quick, and then you pass out and you forget. Then you get it out the next day, it's kind of exploded, because as the liquid became solid, the solid takes up more space than the liquid. So it turns out that's why Ice floats. Ice floats because in the solid phase, it's less dense than it is in the liquid phase. It's less dense in the solid phase because the spacing between solid water molecules and the spacing between liquid water molecules is the space between the liquid ones is less. So it's a little more dense in the liquid phase than it is in the solid phase. But okay, so in any event though, what we're seeing here is that when you have different phases of matter, there is different degrees of attraction between the entities that make up those forms of matter. The massive, most obvious, biggest attraction that they exert on one another is when they're in the solid phase. That's what makes them solid. It's what holds a chunk of it together. Then intermediate, there is a phase known as a liquid phase. In the liquid phase, molecules are just about as far apart as they are in the solid phase, but because they have less attraction for one another, you can now part them. So you can go through a liquid, but you can't so much go through a solid. Now, again, yes, you can go through a solid, but you have to exert a little bit more push to push your way through the solid. Now, finally, if you get to the gas, not only is there less interaction in a gas compared to a liquid, there's also a great amount more space taken up by the molecules. There is a lot of empty space between molecules in a gas phase compared to how much there is present in either the liquid or the solid. So not only is there a lower attraction when you're in the liquid phase, or I'm sorry, when you're in the gas phase, there's much more space between the molecules. This is why you can see a liquid. I mean, when I have a jar, but I can see it because the molecules are bunched so closely together that I'm looking, literally, when I look at the liquid, I'm looking at trillions upon trillions of liquid molecules. But when I'm looking at a gas, yes, the interactions between them, again, are weak. They're weaker than they are in the liquid state, but now the molecules are so spread out relative to each other that I can't see a bulk collection of them and see them as something my eyes can pick up. Okay, so essentially then, when we have the solid form, or let's put it this way, anything that's being ionic or an ionic compound is typically going to be a solid. Anything that is a molecule is either probably going to be a liquid or a gas. Now, I can't say that that's entirely true. There are exceptions to this rule. There are many solid molecules as well, but for the simplest way of thinking about it, we'll go with the fact that solids are ionic compounds and liquids and gases are generally, just for ease of thinking about them, they're going to be more molecular in their form. Okay, so then I think I have one more statement down here. Typically, molecules are formed when nonmetals or these things we call metalloids that are close to them combine with themselves. Now, I did have a slide a long time ago that showed the differentiation in the periodic table between metals and nonmetals. I don't think I repeated here, so that's unfortunate, but I guess I didn't put that slide in again. Okay, now, when you name molecules, we talked a little bit last time about naming compounds. You always state the name of the cation first, you state the name of the anion second, and you change the ending of the anion to IDE. So when you combine sodium and chlorine, of course, you call it sodium chloride. When you combine magnesium and fluorine, you call it magnesium fluoride. The IDE ending is given to the anion to change its name. Now, when you do molecules, we do those same things. We do have something that's going to be a negatively charged thing that's always going to be the IDE ending, and something that's kind of positively charged that has a name that's not changed. But in the case of molecules, we typically use prefixes to tell us how many units are in the molecule as well. Now, these are the first 10 of those prefixes that we use when we're naming molecules. Now, okay, this, what I should have put as an extra word in here, this is how we name so-called inorganic molecules. Now, what do I mean by inorganic molecules? Essentially, it means as long as they don't have carbon and hydrogen. Molecules that have carbon and hydrogen, as we're going to see shortly, we play a different game. If they can still have carbon with oxygen, they can still have hydrogen with nitrogen and things of that sort. But when you put carbon with hydrogen, we call that an organic molecule. And the organic molecules have their own naming schemes. And we don't use what I'm showing here as the typical scheme of these name prefixes. So these prefixes help us tell in the molecule unit just how many of each type of atom are present. Once again, the thing you name first does not have its name changed. The thing you name second has an IDE ending, just like we did for sodium chloride. So here's just some examples of some names. If I have silicon tetrachloride. Now, this differs from sodium chloride because I'm told in the formula that I have tetrachloride, which means there, as you can see from the formula, there are 4 chlorines hooked to a silicon. If I give the name carbon monoxide, now remember I said that this is an inorganic molecule because instead of having carbon and hydrogen, it has carbon and oxygen. And it has a carbon with a single oxygen, that is carbon monoxide. Then if I go further, I can have sulfur trioxide, that would be S with 3 O's. This would be a dinitrogen pentasulfide. If I have multiple first atoms, I put a prefix on that one as well. And here's, again, 4 phosphoruses hooked to 10 oxygens. Technically, this would be called tetraphosphorus decoxide to give the name telling us how these are connected. Now, one of the things you should note about these, maybe you don't because we don't have a periodic table, but these are all non-metals combining with non-metals. They are not metals combining with non-metals. Typically, molecules are formed when you have non-metals combining with themselves. Now, what are non-metals? There's a little staircase in the table of elements, and the elements above the staircase are the non-metals. And when you combine them together, a couple things happen. They don't concatenate over and over again. They form individual units, and we give them these specialized names as a result. Okay, just a couple more, maybe a familiar one at first, carbon dioxide. Now, let me just mention something very interesting about carbon dioxide, and on this other slide, carbon monoxide. This is one of the reasons why the prefixes are used, because carbon readily combines with oxygen under certain conditions, and it easily can form either carbon monoxide or carbon dioxide. Now, carbon dioxide, as you can see, is CO2. Carbon monoxide, as you can see, is CO. Now, just a point of interest. I'm sure everyone has heard the names carbon monoxide and carbon dioxide. Let me just point out a few of their features. They both are carbon-oxygen combinations. One is a carbon combined with 1 oxygen, of course, carbon monoxide. One is a carbon combined with 2 oxygens. That would be, of course, carbon dioxide. Now, the other thing of importance is that they're both gases. So they both have molecular forms where they're combinations of C's with O's that float around independent of each other. And of course, being individual molecules, as I breathe in and breathe out, I can certainly breathe in and breathe out carbon monoxide or carbon dioxide. Now, then, as a point of interest as well, they are both clear and colorless gases. They are both odorless gases. You would never know they're present. So you can breathe them in routinely and never know the difference. But there is one very important difference between them at the atomic or at the so-called molecular level. Carbon monoxide tricks your body. When you breathe in enough carbon monoxide, it goes into your lungs, and waiting in your lungs at the very small capillary level of where the blood in your body reaches your lungs, there's components of your blood sitting in your lungs waiting. And those components of your blood are the hemoglobin molecules. So hemoglobin sits right at the edge of where the air comes into your lungs, and what it does is attaches an oxygen molecule out of your lungs. So it's kind of like pulling up at the sonic drive-through. The hemoglobins in your blood file up to your lungs and sit and wait in your lungs. And then when an oxygen comes into your lungs, the oxygen attaches to the hemoglobin. Then the hemoglobin drives away and goes to various regions of your body and is sucked through the walls of the cells of your body, feeding your cells oxygen. Oxygen is the fuel that drives the reactions in your cells that make it possible for me to stand here and think, stand here and wave my arms, stand here and move my jaw muscles, and make it possible for me to spit air that bends and wiggles and goes down your ear canals, and you hear it, and then you can transmit that into the communication of what I'm saying to you. So all this craziness occurs because there are hemoglobins waiting at the train station to pick up O2 molecules and carry them to your cells. Well, let's suppose that at the train station, a CO pulls in instead of an O2. Unfortunately, hemoglobins are not smart enough to say, that's a CO, I don't want that, I'm going to take it. So COs can pull into the train station and attach to your hemoglobin just like O2. And the hemoglobin doesn't know any different. So the hemoglobin drives away, carries it to the cell, delivers it to the cell, and the cell says, I don't know what to do with this. I only know how to work with O2. So if enough hemoglobins pick up enough COs in your lungs and carry them to your cells that are starving for O2s in order to get the energy they need to do the stuff that they want to do, you're in trouble. And you get carbon monoxide poisoning. Now, this does not happen with carbon dioxide. It's just carbon monoxide that is able to trick your hemoglobin. So that's one of the insidious and important differentiations between these molecular forms. Again, carbon dioxide and carbon monoxide are both gases. Carbon dioxide and carbon monoxide are both molecules. Carbon dioxide and carbon monoxide are both clear and colorless and odorless. And you can never tell them apart when they're present in a room. But carbon monoxide, lethal. Carbon dioxide, well, okay, it's not great. It does other bad things. Don't get me wrong. It does do some bad things. But one thing you can do is breathe it in and breathe it out. And it ain't going to kill you. Okay, so why in some instances is carbon dioxide form compared to forming carbon monoxide? It depends on the conditions of a reaction, say in particular in a fire. Under certain conditions of burning a fire, when the oxygen to carbon ratio is correct, you will make carbon dioxide as a result. When the oxygen to carbon ratio is incorrect, you will make carbon monoxide as a result of burning organic materials like wood. So that's where the problem lies with something like carbon monoxide compared to carbon dioxide. Now, okay, I got into a lengthy diatribe there about that, but I just thought that was maybe of some interest to some of us. And you know me, I like to ramble about things I think that are things that maybe we have some knowledge of, but maybe we don't have intimate knowledge of. Okay, so the other things I'm just showing on this slide, these are not things that want you to memorize or anything like that. If I asked you anything at all to do with any of these, you could always just look up the prefixes on the previous slides and figure out what the names of these might be based on what element is combining with what element and how many of them are in combination. So if you saw something like I2O5, you could turn to the periodic table, find out that I is iodine. Since there are two of them present, then you have to put the prefix in front of it that means two, and the prefix that means two is di. So I would call it diiodine, and then the second atom being an O, and there are 5 of them. First, the O means that it's oxygen, but because it's the second thing, we always change the name, as you'll notice all the way down the list. The name of the second one is always IDE. That's what we do when we combine atoms together. We make the second one an IDE ending. And there are 5 of these oxygens present, so it has to be a pentoxide, as you see there for the name. I2O5 is diiodine pentoxide as its molecular name. All right, now what we're going to do is then look at the special case of when hydrogen is present in the molecule. So when hydrogen is present in molecules, they don't go by these prefix names. Never. When hydrogen is present in the molecules of this type, they go by traditional names. The first two, of course, are very familiar to us. Well, maybe the first one for sure is familiar to us. We never call that molecule dihydrogen monoxide, which is technically what it should be. Now, as a matter of fact, if you go online and look up the dihydrogen monoxide, some people try to be clever, make up funny stories about purchasing dihydrogen monoxide or the lethal nature. More people die from ingesting dihydrogen monoxide. I guess they drown than many other materials. So there's lots of funny people that make jokes about that online. Nitrogen trihydride is never called nitrogen trihydride. It is always called ammonia. And then the last one, we might think that would be called carbon tetrahydride. That is always given the name methane. Now, the last one in particular, we're going to spend a lot of time on as we move into carbon-containing combinations that are molecules on the next couple slides. So anytime you see molecules with hydrogen, because they've been around for a long time, because they were used by humans a long time before we systematized the way we name them, so we go with their traditional names. The traditional name of H2O has always been water. Of course, in Spanish, it would be agua. I'm sure there's something else. It's agua. In Spanish, it's aqua. In French, I'm sure other things in other languages as well. But we don't go with the technical name that the chemical formula says we should go with. Okay, so organic molecules that contain hydrogen and carbon have their own unique naming scheme. Now, we don't need to focus on those right here on this slide because I'm going to bring that up again later. When they have carbon and hydrogen, they have their own names. But if they are inorganic molecules, and again, I'm going to back up here, these are so-called inorganic molecules that don't have carbon and hydrogen, then we will use the prefixes. Okay, now let's then turn to the interesting combinations that carbon likes to make. So first of all, let's define the specific carbon chemistry as being called organic chemistry. Now, of course, the name organic chemistry comes from the fact that anything in a living system has a certain types of chemical reactions, and the basis, foundation, element involved in essentially every reaction in living systems has carbon-based molecules. So organic chemistry is the chemistry of carbon-based molecules, and since living systems have organic molecules or carbon-based molecules that make them up, and the word organic means something with regard to living, then organic chemistry has come to be known as the chemistry of carbon-containing molecules. Now, carbon is very unique in its outer spread of electrons around its nucleus. There are 4 of them. Now, this is not the total of all the electrons on carbon. There are actually 6. But what we can envision is that the electrons come in layers. There are 2 inner layer electrons, and there are 4 outer layer electrons. Now, earlier in this period, I talked with you a little bit about the difference in how molecules connect compared to how ionic compounds connect. Again, as a reminder, ionic compounds have a giver and a taker. And the giver and the taker either become a cation or an anion. If they give, they become a cation. If they take, they become an anion. And then electrostatically, they stick. Now, molecules, on the other hand, share. And carbon has 4 electrons to share, meaning all carbon atoms are willing to give electrons to other atoms, and they have 4 of them to give so they can connect to 4 other atoms. Well, let's put it this way. They can in some way share these 4 electrons with other entities, as we will see here. So let's look at the way carbon can share its 4 electrons. So it has these 4 so-called valence electrons to share, and carbon is very effective in, as we say, covalently bonding to itself or others, meaning covalent, meaning sharing electrons with itself or others. So let's take a look at when carbon bonds to another carbon. Notice envision it this way. I take 2 of these carbons with 4 dots around each. Carbon on the left kicks a dot onto the poker table. Carbon on the right kicks a dot onto the poker table. I connect the dots, if you like, the carbon on the left put in to the carbon on the right put in, and I make a chemical bond. So the line I'm using to connect carbon left to carbon right in this picture is called a chemical bond. And what the chemical bond represents is an attachment that the carbon on the left is making with the carbon on the right. Now, I want to point out to you with no uncertainty, this is not an ion. The carbon on the left is not positive, while the carbon on the right being negative. Carbon on the left is not negative, while the carbon on the right is positive. They are both neutral. So these are not ionic bonds where opposite charges are pulling them together. This is a sharing bond. And anytime you see chemists connect the symbols with a line, you can assume that one of the carbons on the left has put an electron in, and the carbon on the right has put an electron in, and they are connected together by a chemical bond of 2 shared electrons between the connecting atoms. Okay, so a singly bonded carbon has 3 remaining connections on each carbon. Notice that. Now then you can have a so-called doubly bonded carbon. Now what does it mean to be doubly bonded? Let's start with the top picture where each carbon has 4 electrons to give. And on the picture I'm showing at the bottom, each carbon only has 2 remaining electrons. What that means when carbons double bond is that each kicks in 2 electrons each. So there are 2 lines. Each line represents a shared connection of electrons between the carbons. So when carbons doubly bond, they each kick in 2 electrons, so that there are 4 electrons shared between them. Now carbon can go a step further. Carbon can do some trick like this as well. Now let's understand what that picture represents. It starts with 4 each. Each only has 1 remaining dot. Where did the other 3 dots go? Again, did they get swept under the rug of the universe, thrown into thin air? No. Each of the remaining 3 dots is shared with another carbon. So what we would claim in the bottom picture is that carbon is triply bonding to itself. And carbon is incredibly prolific at all 3 of these types of connection. Carbon can singly bond to itself, share a single electron with another carbon. Carbon can doubly bond with itself, share 2 electrons with another carbon. Carbon can triply bond with itself, share 3 electrons with another carbon. Now, as the things in red say on the right, when carbons singly bond to other carbons, they still have 3 remaining dots, meaning they still have 3 remaining attachment points. So the carbons still can combine with 3 other connections each. Now let's go to the middle picture. When carbons double bond, they take 2 of their 4 dots and share them with another carbon, giving 2 of its 4 dots. Each carbon has 2 remaining connection points. So when carbons doubly bond, they have 2 remaining bond sites. Then finally, when carbons triply bond, to triply bond, they each have to put 3 in. They had 4 to begin with. Each carbon has a leftover attachment point. So each carbon has 1 remaining bonding site. Now, what we can then do is start to extend this to multiple connections of carbons. Now, one thing I will point out before we move on is hydrogen is a little different. Hydrogen only has a single dot. Hydrogen does not have 4 dots. Hydrogen is the first element, has only 1 dot. So hydrogen can single bond to carbon or single bond to itself, but it cannot double bond. It cannot triple bond. And once hydrogen single bonds, it has no more remaining attachments. It only has 1 attachment to begin with. So hydrogen can form a single bond only. It can single bond to itself, or it can single bond to carbon. Once a hydrogen single bonds to carbon, then there's no more attachments for the hydrogen. It kind of terminates the chain. So let's see what that means going further on some upcoming slides here. Okay, so before we move, maybe I should say one more thing. The attachment points can be hydrogens, yes, but they can also be other carbons. So what happens if you concatenate carbons in a line of more than 1? Well, we name the chains by these prefixes. Now, these are a little bit different. Some of them are the same, but a lot of them are a little bit different than we use for the inorganic molecules. In particular, the first 4 are different. I think the remainders are the same. 5, 6, 7, 8, 9, 10, 11, 12. Those are exactly the same prefixes that we used in the inorganic molecules. 1, 2, 3, 4. 1 in the inorganic world was mono. In the organic world, or in the carbon world, it's meth. 2 in the inorganic world was di. 2 in the organic world is F. 3 in the inorganic world was tri. 3 in the organic world is prop, not prop, prop. 4 in the inorganic world was tetra. 4 in the organic world is bute, not but, bute. Now, again, 5, 6, 7, 8, 9, 10, and actually 11 and 12, same as they are in the inorganic world. So why are the prefixes, now again, what are the prefixes used for? To tell you the number of carbons in the molecule. Why are prefixes 1, 2, 3, and 4 different in the organic world than they are in the inorganic world? It has to do with the fact that these sciences developed independent of one another. People began naming the organic molecules independent of the organic molecules because they didn't realize there were connections between them until it was too late. The names got really popular for the organics. They got really popular for the inorganics separate from one another. And then when they tried to put everything together to give a single picture of the story, there was too much confusion because one group wanted to use one set of names, one group wanted to use the other set of names, so they just kept their original names. So again, everything above 5 is the same, but the first 4 are different prefixes. What do the prefixes again reference? How many you concatenate. So let's look at how to use these. And the first ones we're going to define are molecules that are in the organic world. Now, we're speaking explicitly organic kinds of molecules. Some of these names, I hope, look very familiar to you because I'm sure you've run across them in various commercial applications. They have a lot of very common usages in various parts of commerce and society and technology. So the first kind of carbon organic molecules we're going to discuss are what we call alkanes. Alkanes are hydrocarbons. Now, what does it mean to be hydrocarbon? You only have carbon and hydrogen. And when you have carbon and hydrogen, you have your own unique naming scheme, unlike the inorganic names. They are all connected with a single bond. Now, the key to this is the ending. When the ending is ANE, that means the carbons are connected with single bonds. Again, what does it mean to be a single bond? Each carbon puts one electron on the table, and they share that electron. Single bond, one electron each, 2 electrons total. Chemists draw it with a straight line. Straight line means connecting 2 carbon atoms, each with a single electron. Okay, so here's some names of these molecules. Okay, so here's how you would name these molecules. You use the appropriate prefix to indicate how many carbons are in the chain, and then you attach the ANE ending, which means all the C's are singly bonded. And then what do you do with all the other spots? You put H's on them. All right, so we're going to look at some examples of this. Remember, all carbons have 4 connections. The carbons are singly connected to themselves, and then the remaining connection spots are connected with hydrogens. Here's what we mean. Methane. Meth means 1, all single bonds. So 1 carbon, all single bonded. So I'm going to attach to the 4 connection points of the carbon a single hydrogen. So there is a single bond or a share of an electron from a carbon to a hydrogen, carbon to a hydrogen, carbon to a hydrogen, carbon to a hydrogen. So this molecule is often called natural gas. It comes from the earth, very commonly in processes where plants are mushed together by the geological pressure of the earth, squeezing on them. Decaying forests that kind of got smashed into the earth during crazy seismic events on the earth, like cataclysmic splits of the earth where sections of the earth got folded upon themselves, things like that. The organic matter in the earth got squeezed together in pools by the massive amount of weight of the earth, and the organic vegetation and animals and critters and stuff kind of dripped together into a puddle of goo. And the puddle of goo in the center of the earth, or not all the way in the center, but somewhere in pockets of the earth, has ended up mushing over the eons of time together into masses of these organic chemicals mixed together. And probably the most prevalent of all the things in the mixture are this material known as methane. Methane then gets squeezed. It itself wants to be a gas, so it kind of squeezes its way out through certain types of rock and gets spread through layers of it in the center of the earth. And it is then what we call natural gas, which can be released from the earth and released from rock formations after it's been squeezed into this form after thousands, if not millions of years of being pushed on by masses of rock in the earth. Okay, now again, meth means one carbon. Ane means single bonds. If there's only one carbon and that carbon has 4 attachments, you single bond it to a bunch of H's. So the formula, of course, for methane is CH4. And this is as simple of a hydrocarbon as you can get, of course. 1 carbon, 4 hydrogens. Now, the chemical formula, as I said, CH4, and the carbon has 4 lines coming from it. Now, this is the secret of all anes. Every ane molecule that we're going to show after this, and I'll point this out many times over. Notice how there are 4 lines touching the carbon. To a chemist, each line represents 2 dots or 2 electrons. So there's a 2 electron line from the C to the H to the left, to the C to the H above, to the C to the H to the right, C to the H below. 4 dots from the carbon shared with 4 individual dots, 1 from each hydrogen. So the formula for that simplest hydrocarbon is methane. Now let's look at the next simplest one. What I will do is I'll start with a methane. I will pop off an H, and then I will slide on another popped off H. So this is a connection on the bottom. What I'm showing is the next simplest hydrocarbon. First of all, it is an ane. Why is it an A-N-E ended hydrocarbon? Because it has all single bonds. Notice there's a single line attaching all atoms connected to each other. There are 2 carbons in the line. So 2 carbons use the prefix, not di, they use the prefix F. So this is an F molecule. And each carbon, of course, after it attaches, has 3 remaining attachment points. On the 3 remaining attachment points, you put hydrogens. So I could just draw the line between the C's, and let me back up for a minute. Maybe I'll show you what I mean by that. If I back way up to here, not to there, sorry. I'm sorry that I'm going, okay, here. Let's look in the middle of my screen. And I'll see if I can get my arrow to cooperate. Here's my arrow. Here's the middle of my screen. I have taken from this 4 dots situation, 1 dot here from this carbon and 1 dot from another carbon, and down here in the middle, I've connected them. Now notice connecting 1 dot from each, there are still 3 dots on the carbon on the left. There are still 3 dots on the carbon on the right. So what I'm going to claim is I'm going to attach an H here, an H up there, an H down here, and on the left carbon, an H at the bottom, an H to the left, and an H to the right. So there's 3 attachment points for H's on the left carbon. There are 3 attachment points for H's on the right carbon. And when I do all that, now I'm going back, a long way back, several slides back, and we're almost there. When I do that, I will get this molecule, ethane. Ethane is either given the name CH3CH3, or if you put all the atoms grouped together at once, it could be C2H6. Now again, chemists, depending on which chemist is writing the formula, some of them write that with all the C's grouped together and then all the H's grouped together. You count that up, it'd be C2H6. Some chemists like to show how each carbon group is connecting, and that is doing so with a CH3 on the left connected to a CH3 on the right. So some people, again, depending on your desire or your taste, might name ethane C2H6. Some people might name it CH3CH3. Now, we can just continue this idea, and you can go to propane. Propane, again, should be a familiar name to you if you do any outdoor gas grilling. This is the kind of gas that is present in the grill. Now, what does prop mean? If you go back to my prefixes, it means 3. So now I'm going to attach 3 carbons. And the ane meaning that you single bond all 3 carbons to each other. So what I will do is I will connect it like this. Let's make sure that we're clear what this is meaning. Ane means single bonds. That means one line connecting all the H's to the C's to everything else. The prop means 3 carbons in a line. So first I connect 3 carbons by a single line. Notice the middle carbon, after connecting to the 2 outer carbons, only has 2 attachment points left. The 2 outer carbons connect to the middle carbon. They each have 3 attachment points left. So the N carbons each have CH3 around them. The middle carbon only has CH2 around them. So propane, all carbons have 4 attachments. Because the middle carbon has attachments to 2 C's, it only has room for 2 H's. Because the 2 N carbons have attachments to only 1 C, they have room for 3 H's. So the formula for propane, depending on your taste, you can either count up all the carbons and all the hydrogens, group them together, and get C3H8, or you can do it in individual units. So to do it in individual units, some people would prefer to write CH3 is connected to CH2 is connected to CH3. So again, this depends on what you prefer as your desire to write them. Now again, where's some uses of propane? Well, if we liquefy it, particularly if you put it under high enough pressure, it's a liquid, so we call that LP. Then you put this LP into a tank, it's liquefied propane. Then when you open the valve, as it escapes out of the valve, it becomes gaseous propane. It's a very familiar fuel. The reason we prefer it over methane is really hard to liquefy. So this can be easily, ethane, again, is hard to liquefy. Propane is easy to liquefy. And when it's in the liquid form, you can pack a whole bunch more propanes together than in the gas form. In the gas form, as I talked about before, gas molecules spread further apart from one another. So you'd have to have a huge tank of gas phase propane to run your grill. But if you liquefy it, you literally are packing all the molecules really close together. Now, when I open the valve, they come out as gas, but most of them still remain liquid in the tank. So you can store liquefied propane in a much smaller space than you can store gas phase propane. And the reason we use liquefied propane is that it's way easier to liquefy propane than it is to liquefy ethane or methane. You have to use crazy high pressures to liquefy either one of those. Believe me, the propane's bad enough. That tank is under pretty good pressure, and if you get in trouble with it, it can be explosively high pressure. Okay, sorry, it looks like quitting time. Next time, we're going to continue to play with more of these organic molecules and their nomenclature and their uses. And then we're going to do some plastics. Okay, so till next time, peace out.